characterization of stand dynamics, and estimation of future stand conditions. The more practical objective for this project was to then use the equations developed into existing growth and yield models, such as MGM, the mixed with growth model developed by the University of Alberta, and GYPSY, which is the official growth and yield model used by the province of Alberta to develop all the timber supplies assessments. So the real value of this data is probably with of this project is probably with the data. I was lucky to work with a very large data set, which included the PSP data, the permanent sample plot data from a number of provinces, including Alberta, British Columbia, the Yukon, Northwest Territories, Saskatchewan, Manitoba, and also from the United States for Alaska. And within Alberta, I not only had the data, for the province, which is ESRD in this list, but I also had the data from 4 forest companies. So in total, I was able to develop the functions for 7 major tree species, thanks to over 11,000 PSPs, more than 1.2 million trees, and a total of over 2.5 million observations. So we can now have a look at the distribution of the PSPs within the data set. So each one of these black dot is a PSP. And we can look also at the breakdown by the major 7 tree species that were selected. So we have white Engelmann spruce with over 7,000 PSPs, and here at the bottom we have the map with the range of the PSPs. And we have black spruce with over 4,000 PSPs and the range. For lodgepole pine, we almost have 7,000 PSPs and the relative range. For jack pine, we had fewer PSPs, only 533. For balsam fir, we had over 1,600 PSPs. For trembling aspen, just a little over 4,800 PSPs. And for balsam poplar, over 2,400 PSPs. So the PSP data provided information about the species composition within the permanent sample plot. And we also had measurements for DBH and for subsample for height. So using that data, then I could calculate a number of competition estimates. And then we went a step further, and we also generated a number of climate variables using a software called Climate NA, which interpolates data from weather stations. So we had some basic climate information like temperature and precipitation, and then we calculated a number of climate indices, such as the climate moisture index developed by Ted Hogg, which has proven in many studies to be an effective way to quantify the climatic conditions on the stand. So now we had all the ingredients, we could test them and develop the model. So the model was investigating the survival probability in relation to tree size, either DBH or height, competition by species groups. So the tree species were grouped by all the pines together in one group, all the deciduous species in one group, and then spruce and fir were combined in a third group. And for these groups, we calculated a number of estimates, competition estimates, such as density, the sum of the DBH for the trees thicker or taller than the subject tree, and basal area of the larger trees within the plot. So for climate, we screen all those variables, and it's important to mention that only one average value was used per plot. So we only calculated the normal period between 1981 to 2010, and we had one value per plot. And then other variables that were important and included in the model were the time length, which is the number of years elapsed between 2 consecutive measurements. So obviously, the longer you wait to remeasure a stand, the more likely you are to find a tree, and that had to be taken into account. And the tagging limits, because all these different agencies have different measuring protocols. Therefore, that was also included in the model. There are some agencies that measure every tree at DBH height and above. Some have cutoffs at 5 centimeters DBH, some other at 7, and so on. So that was also included in the model. So now we can have a look at the actual model that was selected at the end. So it's a logistic model, the probability of survival, Greek, like more Greek, and then the power is L, which is the is the time elapsed between two consecutive measurements, and the C component in the model breaks down into an intercept. For tree size, DBH was selected in the final models instead of height in a quadratic form. And then we have our competition estimates. We have basal area of the larger trees by species groups. Our climate variables was CMI, the climate moisture index, and also we have the tagging limits as well. So now that we have the model, we fit this model for the 7 tree species, and we can start looking at the results. Fine. So here are the results for DBH. So this graph is showing the survival probability as it changes as DBH increases. So the other variables in the model were kept constant at the average value. And we have our 7 species. SW is white spruce, SB is black spruce, PL is lodgepole pine, PJ is jack pine, AW is rambling aspen, PB is balsam poplar, and FB is balsam fir. So we have the typical reverse U-shaped pattern, typical when DBH increases. So basically at low DBH values, mortality is high, the probability of mortality is higher, and then I got it reversed. Survival probability is low, and then increases as the DBH increases, and then it plateaus, and then it drops again as the tree becomes older and DBH becomes increases. And this pattern follows the ecophysiological characteristics of each tree species. Then we can move on to the results for competition. Here is for the spruce fir group. So we can see that for every species, as the competition from the spruce fir group increases, the survival probability decreases. Then it's, for instance, jack pine, which is a pioneer species, very shade intolerant, which appears to be very strongly negatively affected by competition from the spruce fir group. Likewise, from competition from the sedges, we see that for every species there is a decrease in survival probability as basal area increases on the stand, and it follows the path of the characteristics of the species. For the pine group, we have a negative effect on the 2 pine species, indicating an almost strong negative intraspecific competition, effect of intraspecific competition. And for the other 3 species that were significant, where pine was significant in the model, there is a flat, if not very minor, increase in survival probability. The next graph is about the climate variable. For all species but the pines, we have an increase in survival probability as the climate index increases. This increasing climate index means that the weather gets cooler and wetter. So all the species but the pines benefited in a sense. The plots that had wetter and cooler climate benefited in terms of survival. So when we develop the model, we use 90% of the data randomly selected up front. And we put aside 10% to use at the end to validate the models. When looking at performance measurements for this type of analysis, there's two typical measurements that we look at. One is the rock curve, and the other is the AUC, the area under the curve. The rock curve is basically a curve generated by plotting the number of times that the model gets it right in predicting the population data set against how many times it gets it wrong. And we do that at various threshold settings. And the AUC is the area under that curve. Now, it should make a little more sense if you look at these 4 examples. So we have scenario A, B, C, D, and those are all rock curves. Scenario A is the best case scenario. So the AUC equals 1.0. In other words, if your rock curve looks like scenario A, your model was 100% of the time correct in predicting the survival probability of the validation data set. The worst case scenario is scenario D, and your AUC is only 0.5, which means that your model was only 50% of the time correct in predicting the validation data set. And that will be the same probability of the coin toss. So obviously you don't want your model to be as good as a coin toss. I don't think Phil will be happy with that. So now we can look at the results. We have the results here are our rock curves for the 7 species, and you can see that luckily they look more like scenario. They're closer to scenario A than scenario D. And if we look at the specific AUC, the area under those curves, we can see that they range between 0.81 for balsam fir to 0.90 project time. And the overall average of this AUC is 0.85. So our models were 85% of the time correct in predicting the validation data set. So all this work just last week was finally accepted in the Forest Ecology and Management Journal for publication, so it should be available in the next few weeks. And that's it for me. And you have any questions?
Question?
You didn't try other mortality shape like a log function or some other?
Not really, no. We went